So first of all, that means it can't be a polytope. It can't be bounded. Because as soon as you put a point in the cone, you have to put the whole ray off to infinity. So if I put this point in there, then I have to have the whole ray and everything in between. So in the plane, a cone is just like a wedge like this. Or, for example, this is also a cone. Because, I mean, so that's the defining property. If V is in the cone and lambda is bigger than 0, then lambda V is in the cone. And so you do have a notion of kind of the corner, and then it's just rays from that corner. Except the corner might not be well defined in a case like this. This is also a cone. Lambda greater than 0. Yeah. Any other questions about polytopes?
I have about the boundaries.
Uh-huh.
Like, if you have a cube, because we use an example of a square, and I wouldn't know how to do the boundary of a cube.
Okay. Just a quick announcement that the Algebra Geometry Combinatorics seminar is going to be great today. So the speaker is Renzo Cavalieri from Colorado State and MSRI. And he's a really, really good speaker. And he's going to talk about something very interesting, which I like, because I think I've tried to make this point many times. Sometimes people try to segregate us into disciplines, and this is one of those things where he's going to talk about how to solve a question that kind of comes from analysis. You have to do some, it boils down to some combinatorics, and I think he's going to do a really nice job explaining that, so you should go to that. So the boundary of a cube. So what's your question exactly?
Like the orientation, like the boundary, like, I don't know, the boundary operation, like when you
Oh, I see. Yeah, I think that's a more subtle question that I can answer quickly. So it's the question of how do you orient something. I mean, it's kind of the right-hand rule idea. Is what you know, this thing where you go either oriented with your right hand or with your left hand. But to make that precise, I think I can't say that in a minute. So that maybe we can talk about it during office hours, but I will tell you basically that, and this is all we need to know, that there is a way of making it work, so that making the signs work, so that this is a complex, and the boundary times the boundary is 0. And in the examples that we're going to draw, they're either in 2 dimensions, so you just choose clockwise or counterclockwise for each phase, or they're 3-dimensional, and then you do either right-hand rule or left-hand rule. Those are the 2 ways of orienting a polytope in 3 dimensions. I got all chatty, and then I had to find my markers and my notebook and everything. But this is good. Any other questions about polytopes? I mean, polytopes are something that are maybe intuitively kind of clear, but the danger is to trust your intuition too much, right? Because we have very concrete ideas about what happens in 2 and 3 dimensions, and in higher dimensions that might not happen. So, by the way, another announcement is that I've had your homework for like a week, and every time I bring it in, I forget to give it to you. So please don't leave without me giving it back to you. Okay. So where were we? We were talking about labeled cell complexes, right? So just remind you of that definition. A labeled cell complex is X is a polyhedral complex. When I write CX, I mean complex, with vertices labeled by monomials. X to the AI for each vertex vi, so and then once you have the vertex labels, that gives you uniquely labels on every face. And face F is labeled by what? Well, we talked about what it means to be a vertex of a face, right? To be a vertex of F. And so what you do is that you consider all the vertices of your face, and you take those exponents and you take the LCM of these things. Okay? And so we did this example where maybe we choose to label the vertices a squared b, b squared c, c squared d, d squared a. Okay? And then that uniquely determines what we should label everything else. So for example, this face is going to have to be labeled b squared c squared d, and c squared d squared a, d squared a squared b, a squared b squared c. So those are the labels on the edges. And then I need a label on the square, which is the LCM of all the four things. So that's a squared b squared c squared d squared. Okay? And this brings me back to Thomas's point that when I drew this, I didn't fill it in, and that is confusing. So really what I meant is for this to be a full square. So that's a labeled cell complex, and then we said that given that, you get something called the cellular free complex. X supported on X is something that is, I think, clearer by example. So it's a it's the chain complex where what you do is that you put the empty face here, the vertices here. So for example, here you get shifts of 2, 1, 0, 0, 0, 2, 1, 0, 0, 0, 2, 1, 1, 0, 0, 2. So these are the vertices. Then here you put the edges. There's 4 edges, and they get shifts of 2, 2, 1, 0, 0, 2, 2, 1, 1, 0, 2, 2, 2, 1, 0, 2. And then the two-dimensional faces, there's only one, and it has shift 2, 2, 2, 2. Okay. And the way that you get maps from here is using the boundary maps, which are just the usual thing we did in the simplicial complex. We just generalize it in this case. Okay. So, and I stated that this is a chain complex. Okay. But again, Laura's point is very valid that I've been a little bit sketchy telling you how to orient things. And what I will say is that in high dimensions there is a way to make this work. In the pictures that we're going to draw, and the examples that we're going to see, which are in 2 or 3 dimensions, you just orient each edge up or down, each face clockwise or counterclockwise, and each three-dimensional face either by the right-hand rule or the left-hand rule. And then you let the boundary maps reflect that. That's how you get the signs. Okay? So I can write this for any labeled polyhedral complex, right? I just drew something, I put some monomials, and I write some complex here, okay? But of course, what we're interested in is we want to do this in a way that this guy will be useful to us, okay? And these things are most useful to us when they are exact, okay? So that's basically what we want to know. So we're going to say that this is a cellular resolution if it is acyclic, and that means that it's exact except everywhere but the last step. Okay. What do I mean by this? What I mean is that there is not really any hope of being exact right here. But everywhere else, we would like to know if this thing is exact or not. Okay. So here's the main theorem about this. So the main theorem is that the cellular free complex Fx is a cellular resolution if and only if something occurs. And the condition that we need is that for all multi-degrees B, we're going to define a subcomplex of that thing. Okay. And it is basically going to be the subcomplex of faces whose labels are less than or equal to B component-wise. Okay. So we want the faces of X such that when we look at the label on that face, that should be less than or equal to B in every component. Okay. Well, I haven't told you what I need. So this is a cellular resolution if and only if this subcomplex is always acyclic, has no homology. Okay, so this is the key thing that one needs to check. Okay. So that's the first thing. And the second thing is that when this is a cellular resolution, then it is a free resolution of R mod I, where what's I is the ideal generated by the monomials at the vertices. So what is it that I'm saying here? What I'm saying is this. I'm trying to see if I can get a free resolution out of this picture. Okay? So actually maybe maybe the second part is more useful, or at least a little bit easier. The second part tells you that if this has any hope of being a free resolution, then we know what it is a resolution of. It is a resolution of R mod the vertices. Okay? So that means that I do this picture, I get some complex. If this complex is a resolution, then it has to be a resolution of R mod the vertices, the vertex labels. And what's R in this case? It's the polynomial ring in 4 variables, right? So that's the first thing. If it's a resolution, then this is what it's resolving. Okay? But the second thing is a condition to figure out whether this really is a resolution or not. And maybe it would be useful here to do an example. For that guy. Okay? So we're supposed to check a condition for every B. So why doesn't somebody tell me a B? So first of all, what should B be? When I ask you to give me a B, what am I asking you to do? What B should be some vector in n to the n. And what's n here? I guess I didn't tell you, but n is the number of variables that you have in your thing. Okay? So here we have 4 variables a, b, c, d. So you should be giving me a 4 tuple. So I want everybody to think of a 4 tuple. Okay? And I don't know, Addie, what's your 4 tuple? 2, 5, 1, 0. But everybody should do the same thing that I'm doing with your tuple. Okay? Because we have to check it for all tuples, and so at least we can check 15 tuples. Okay? So what am I supposed to do? I'm supposed to draw that picture. Okay? But now, so this is x. But now you should only look at the faces whose label is less than or equal to this thing. Okay? So watch me do it in my case so that you know what you need to do. For example, is this vertex supposed to be in here? Well, the label here is a squared b, which is, if I write it in this form, it's 2, 1, 0, 0, which is less than or equal to this in every component. So this guy gets to stay. Yeah? Let's see which vertices get to stay. So b squared c is 0, 2, 1, 0, it gets to stay. C squared d looks like 0, 0, 2, 1. The guy is not less than this, so I have to throw it out. This guy, what is it? 1, 0, 0, 2. That guy is not less than or equal to this, so I throw it out. Okay? And you're supposed to do this for every single face. And you'll see that I have to throw out this face, I have to throw out this face, I have to throw out this face, I have to throw out this face. And the only thing, and this guy, the label is 2, 2, 1, 0. So that guy gets to stay. Okay? So x less than or equal to 2, 5, 1, 0 looks like this. Okay? And so this is what I want each one of you to do in your case. Now, what is it that I need to check? I need to check that this guy should be acyclic. Remember, acyclic means that I have no homology. I have no holes in any dimension. And here that's true, right? This is acyclic. There is no homology. But you should also check that for whatever B you chose, you should have no homology. Okay? But if you did it correctly, you will see that that's true. So according to what B you chose, you're going to get a different subcomplex. But the subcomplex is either going to look like this. So the possible xb's, x less than or equal to b's, you either got nothing. If you were really lazy, you chose 0, 0, 0, 0, and you didn't have to do anything. Or maybe you got a vertex, or maybe you got an edge, or maybe you got something like this. That's possible also. Or maybe you got the whole thing. Again, if you're really lazy, you can just choose a huge B, and then you know that everything gets to stay. And I think those are all the possibilities. So I hope no one got anything different from rotations of these pictures. And these are all acyclic. So because these are all acyclic, that means that what I wrote here is a resolution of my monomial ideal. So that's what the theorem says. Okay. So maybe what I'll do is just give you a proof by example of why this is the case. But maybe I'll just write the punchline. So fx is a free resolution of R mod I. So how do we prove something like this? Well, there is something here that is easy to see, which is the following. Like I was saying, there is no hope of being exact right here. And why is that? The reason is that if I want to be exact here, then the image of this map should be the kernel of this map. Okay? The kernel of this map is everything. And the image of this thing is not everything, because the image is basically the things generated by a squared b, b squared c, c squared d, d squared a. Okay? So what am I saying? What I'm saying is that the image of the map delta 0 is, in this case, is, like I said, as a squared b, b squared c, c squared d, d squared a. But in the way that I built this, these are exactly the vertices, and these are exactly the labels on them. Okay? And so that means that the image of delta 0 is just this ideal that I'm talking about here. This is I. Okay. So, two things. First of all, that's why you cannot be exact here unless I is the trivial ideal, unless I is everything. Yeah. Now, if we know that the image of this map is delta 0, then what do we need to put here to make it exact? Well, we need a map whose kernel is I. And that's precisely the map of modding out by I. So if you want to be exact right here, then this is exactly what you have to put. And that's why this is true. If this is a free resolution, then it must be a free resolution of this. There's no choice. Okay? So that's the first part of the argument. That's why this is true. But I want to justify the second part of the argument. And so how do I do that? Well, I want to know if this is exact everywhere else. Right? What it means for this to be a free resolution is that it's exact here, it's exact here, it's exact here. It's exact everywhere except for here.
What's that meant to be R0, is it? Maybe R1?
R1, yeah, thank you. R1 corresponding to the empty phase, which remember we always put in every polyhedral complex. Okay. Thank you. Okay, so I need to know if this is an exact sequence over here. Now, what does this mean? Well, remember that actually this is a graded complex, right? Every one of these maps stays in its own degree. Okay, and so if I want to be exact all the way over here, then I better be exact for every degree. Okay? For that degree, for example, for 2, 5, 1, 0. If I look at the things that have degree 2, 5, 1, 0 here, and the ones that have degree 2, 5, 1, 0 here, and the ones that have degree 2, 5, 1, 0 here, and the ones that have degree 2, 5, 1, 0 here, then, so maybe this is confusing. Maybe let me call this thing f sub x, which is what I called it, and let me now look at only the things in degree 2, 5, 1, 0. Okay? If this is exact, then this better be exact. Okay? So, how many things do I have of degree 2, 5, 1, 0 here? I have nothing, right? Because the smallest degree here is 2, 2, 2, 2, and higher. So that means that here, this thing gets crossed off. Then here, how many things do I have of degree 2, 5, 1, 0? Well, here I have some things. For example, in my first component, the lowest degree is 2, 2, 1, 0. And so there I have one thing of degree 2, 5, 1, 0, which is called b cubed. So I have one copy of my field given by 2, 2, 1, 0. Do I have anything of degree 2, 5, 1, 0 here? No, right? Because in the second coordinates, my smallest degree is 0, 2, 2, 1, and higher. Here, I also don't have anything of degree 2, 5, 1, 0. So let me just write those things out. This thing gets crossed off. This thing gets crossed off. And now, 2, 1, 0, 2. Do I have anything of degree 2, 5, 1, 0? I don't. So that means that over here I only have one term of degree 2, 5, 1, 0, which is b cubed 0, 0, 0, and its multiples. So that's why I have a copy of the field. I repeat the same thing. So 2, 1, 0, 0, there I do have something of degree 2, 5, 1, 0, so that contributes an f. 0, 2, 1, 0, so there I also have a copy. There I also have something of degree 2, 5, 1, 0, so that's another copy of f. Then 0, 0, 2, 1, then I don't have anything of degree 2, 5, 1, 0. And 1, 0, 0, 2, I don't have anything of degree 2, 5, 1, 0 there. Okay. And here, I didn't write it, but here we'd never shift the first thing by anything. Okay. And so there I do have something of degree 2, 5, 1, 0, corresponding to 0, 0, and then I can stop because I only care about being exact at these three spots. Okay. So what am I saying? What I'm saying is, if I want my complex fx to be exact, and this is a complex of modules, then I need this guy to be exact. And this is a complex of vector spaces. Okay? But if you look at the things that I crossed off here, they're exactly the things that I crossed off in my picture over there. Yeah? These are all the faces that I crossed off. 2, 2, 2, 2 was the square, I crossed it off. These are the three edges going around the square, I crossed them off. And these are the two vertices in the bottom, I crossed them off. And this I kept. And so what I have here is exactly the homology complex of what's left. So this is exactly, this is the chain complex of x less than or equal to 2510. So what I'm saying is, if my cellular free complex is exact, it's because this guy can't have any homology for any choice of B. Okay? So that proves one direction, and then in the other direction, well, if you don't have any homology in any of these guys, that means that you're exact in every degree, which means that that at the level of modules, of graded modules, this is exact. So this is how you prove this theorem. Okay? So again, this is great because basically it reduces the algebraic question of whether we have a free resolution of R mod I to topological questions about this polyhedral cell complex, which is the situation that we like. Okay, any questions about this statement or about this proof? Okay. So maybe I'll just say a sentence about where we are, because remember that basically we are after given an ideal, we want to compute Hilbert series, free resolutions, etc. And we decided that actually the most interesting case for us, and we can reduce to that case, is the case of monomial ideals. And so remember that we said, okay, well, square free monomial ideals, we know what to do. Borel fixed ideals, we know what to do. But now we want to do this for any ideal. Okay? So if I want to do this for some random ideal, for some random monomial ideal, then basically the question becomes, if I have some random monomial ideal, like a squared b, b squared c, c squared d, d squared a, can I somehow find a clever way of building this picture? But I can't just build any picture. It should be a picture where all these subcomplexes are acyclic. And so that's what we have reduced our question to. Given a monomial ideal, can we build a polyhedral complex like this? That's where we are. Okay. So that'll be what we will do next time. But what I want to do today is talk about what if you did manage to do this, like in this example. We did pull this off. So what can I do now? Well, basically the short story is I can run with this. If I pull this off, if I have a resolution like this, then I'm in business because I know how to compute Hilbert series, Betti numbers, all of these things. So that's what we will do next. So before we do that, let me talk about another definition. It's a definition that you might be familiar with, at least in some version, which is the definition of Euler characteristic. So the Euler characteristic of a polyhedral cell complex X is the following thing. So it's denoted by the letter chi, and it is the sum. Basically what you do is it's the alternating sum of the f vector. Okay. This is the f vector, and I just added with signs. So as an example, we have that example over there, right? So the f vector of, did we denote this f sub x? I forget. Well, anyway, the f vector is what? Well, we say there's one face in dimension -1, which is the empty face. Then I have 4 vertices. Then I have 4 edges. And then I have one two-dimensional thing. vertices, edges. Okay. And so the Euler characteristic of this polyhedral cell complex is -1 plus 4 minus 4 plus 1, which is 0. Okay. You might have encountered this in a different class, in a class in graph theory, where they tell you that if you have a planar graph, then the number of vertices minus the number of edges plus the number of faces is 2. And it takes you just a minute to see how that's equivalent to having this be equal to 0. So that's Euler characteristic. So what was Euler doing? He was doing a version of this. If the polyhedral complex is acyclic, then its Euler characteristic is 0. This is in some sense due to Euler. Okay. Like in this case, right? Here I have no homology, so I should expect the answer to be 0. So how do we do this? Well, if X is acyclic, that means that when we look at the chain complex of X, okay, so remember the way that goes is we take a vector space of d-dimensional faces, the vector space of d-1 dimensional faces, etc., up to the -1 dimensional face, 0. Okay. And saying that X is acyclic means that there is no homology anywhere here. So this is exact everywhere. Okay. And now, so is that clear? Remember that basically the homology measures how inexact this thing is. So if there is no homology, that means that this thing is always exact. So if it's exact everywhere, remember we proved this lemma a few weeks ago, that if you have a bunch of vector spaces arranged in a chain complex that is exact everywhere, then when you do dimension of this, minus dimension of this, plus dimension of this, minus dimension of this, etc., you get 0. So when I do that, I get dimension of the first guy minus dimension of the second guy plus dimension of the third guy, etc. is equal to 0. Okay? But what are these things? Well, by definition, f to the fi of x is a vector space where, as a basis, we choose the i-dimensional faces. Okay? So by definition, the dimension of this is the number of -1 dimensional faces. The dimension of this is the number of 0-dimensional faces. Number of vertices plus number of edges minus number of, like this, so on. And so what I get is that this is equal to 0. And this is exactly, I guess, minus the Euler characteristic, but because it's 0, it doesn't matter. Okay. So that's it. Okay. So this is good. You see we're getting somewhere where we can just kind of prove in half a line a nice theorem in algebraic topology. It's good. So for example, one thing that Euler was interested in doing was doing this concretely for three-dimensional polytopes. You might be aware that this is part of how you can classify all the three-dimensional regular polytopes, for example. The thing is that if you have a polytope, a convex polytope, then it has no holes by definition. And that means that it's acyclic, so the Euler characteristic is 0. Okay? And that means that if you take any polyslope, I don't know, what's your favorite polyslope? The dodecahedron, let's say. Yeah, let's do it. What about the dodecahedron? I can't draw it. But I know that the f vector looks like what? Well, the first thing is that it's a dodecahedron, but, well, anything has one empty face. Okay? Now, how many vertices does the dodecahedron have? Do you guys know? Or why is it called dodeca? Dodeca is from the Greek for 12. And what does that 12 mean? It means that it has 12 faces, right? So that we know. So it has 12 faces. Each one is a pentagon. So this is vertices, edges, faces. Now, I know that I have one full dimensional face. Okay. How many vertices does this have? Well, why do you know that it's 20, Lothar? Right, so this is something you need to know, that basically the dodecahedron and the icosahedron are dual to each other. And there's a correspondence where every vertex of the dodecahedron goes to the face of the icosahedron. So if you know that, then you know that this thing has 20 faces. 20 vertices, I'm sorry. But the nice thing is that now I can say how many edges there are without drawing this thing, because I have to satisfy that the Euler characteristic is 0, right? So how many edges do I need to have? Well, I need to put a number so that -1 plus 20 minus that number plus 12 minus 1 is 0. So this has to be 30. So this is an example of how you use Euler characteristic in a very concrete setting. Cool, so that's the Euler characteristic. But we like to grade everything here. Right? We always like to put gradings on everything, and so we're going to do that too. I'm wondering what I should erase. I think I'll erase this. And I think I can erase this also. Yeah. So definition. The n to the n graded Euler characteristic is something that depends on, well, of what? Now I need a polyhedral cell complex, and I need it to be labeled. Okay? And what I want to do is the same thing, except that now I want to attach the monomial to every face. Okay? So what I do is, this thing depends on x, it depends on a bunch of variables. Okay? And what I'm going to do is the same thing over all faces. So I'll write it out, and then I'll explain what I'm doing. So over all faces, I take -1 to the 1 plus the dimension of the face, and then x, and then basically the label of the face. Okay. So again, I think this is clearest if I do it in an example. So for this guy, the Euler characteristic is graded by the variables that I used. And what you do is that you say the same thing. So what do I have in dimension -1? In dimension -1, I have only the empty face, and that empty face has label 1 by convention. Okay. then I subtract the vertices. But I don't just subtract the number of vertices. I have to subtract the names of the vertices. Okay. So I do that. Then I add the edges, but again, I have to add them with their names. And each name is a monomial. Okay. And then I have to subtract the two-dimensional face, which has name a squared, b squared, c squared, d squared. So that is the graded Euler characteristic. Okay. And you can see that this is really closely related to the Euler characteristic. And why is that? Because if you plug in all the variables equal to 1, right, if you let a equals 1, b equals 1, c equals 1, d equals 1, then you're going to get the empty face minus the number of vertices plus the number of edges minus the number of faces. So if you plug in ones, you get the Euler characteristic. It's a little unfortunate that it's off by a minus sign.
Yeah.
That's the convention. It's not my fault. But yes, maybe I'll say this, that if you take the extended one and you plug in a bunch of ones, then you get minus the Euler characteristic. So this is graded and not graded. Okay, so this is the same kind of thing where maybe you care about the not graded version, but we're going to be more ambitious and ask for the graded version. Why do we do this? I'll tell you. The reason we do this is the following. So, theorem: if a labeled cell complex X supports a cellular resolution, and we know that if it's a cellular resolution, then it has to be of R mod I, where I is the ideal of vertices. Then given this, I can easily write the Hilbert series of R mod I. Okay. And I can do it in the fine version. Okay. The answer is amazingly simple. All you have to do is take the Euler characteristic of X, but the graded version of it, and that's going to be what we called the K polynomial. And then you just divide by 1 minus x1 up to 1 minus xn. Okay. So I hope you like this. This is very simple, right? Basically, we're saying if I wanted now to compute the Hilbert series of R mod a squared b, b squared c, c squared d, d squared a. Well, given that we managed to draw this picture, we can just read everything off the picture. You just take this thing, so you put it in here, and you divide it by 1 minus a, 1 minus b, 1 minus c, 1 minus d. Okay. It couldn't be easier. Right? Again, if you think back to what this Euler characteristic is, what you do is basically just draw this picture and write down all the labels for it, and each label comes with a plus or a minus sign. That's the answer. So the other nice thing about this is that the proof is very straightforward from what we've done, because we have a graded Fourier solution, right? Okay. So the way that looks is it looks just like what I had here a minute ago and I erased. Right? So it's the d-dimensional faces, the d-1 dimensional faces, up to the -1 dimensional face. And now this is a resolution of R mod I. So I'm going to put R mod I here, and I get 0. So this is exact. And again, because this is exact, then we have this very nice statement that tells us that size propagates along exact sequences, where size might be dimension, it might be Hilbert series. For example, if we want the Hilbert series of this, then we know that all we have to do is take the Hilbert series of this one minus this one plus this one minus this one, etc. So the Hilbert series of R mod I is just going to be the alternating sum. So this is some sign. We'll see in a second what this is. Times the Hilbert series of each one of these guys. Now what sign should I put? I guess this one gets to be positive, so the sign I should put is I plus 1. Okay. But now, this is easy because each one of these R to the Fi is a free module. It's a graded free module. And so what does it look like? Well, basically, this thing is a free module where you have one component for each face. Okay, so you're summing over faces of dimension I of the Hilbert series of that face. But what is the Hilbert series of that face? Well, basically, that face has a lowest dimensional, lowest generator, and that lowest generator is exactly x to the name of that face. So that's the generating thing, and then everything else is just a multiple of it. So you consider all possible multiples, which gives you this size. So an argument that I'm doing very quickly because we've done similar things a few times, and because I'm out of time. But then you just see that basically we get what we want. We have a sum of the faces of the label of the face with a sign given by the dimension plus 1. That's it. So I think the moral of the story is that if you want to compute the Hilbert series of any monomial ideal, then it's a very worthwhile goal to learn how to draw a picture like this, because once you have a picture, that question is immediate. So we'll see next time how to do that. So I have your homework. Don't leave without it, please.